Hi, this is Jeff Hamrick again at the University of San Francisco's Master of Science in Financial Analysis program. I'm going to talk about the omitted variables test, which is called the OV test, and is sometimes called the Ramsey reset test, and how we implement it in Stata. I'm going to use the same set of data that we used recently for the link test in Stata. It's the built-in set of data called Auto. It's a collection of information about some automobiles, including their miles per gallon and their estimated prices taken in 1978 or some such similar. And let's build a regression model that relates, for example, miles per gallon to weight, displacement, and whether or not the car is a foreign car. So if I regress miles per gallon against weight, displacement, and whether or not the car is a foreign car or domestic car, we get this regression model that we've seen before. And what the OV test will allow me to do in Stata is to examine whether or not a particular class of independent variables would add additional explanatory power to the model. So which class of variables will be considered? The variables that implicitly will be considered would be the second, third, and fourth powers of weight, displacement, and foreign. So the way that Stata will implement this test is by trying to use y hat, the predicted values generated under this regression model, as well as powers of y hat to predict miles per gallon. If those powers add useful explanatory power to the model, then we should go back and consider adding powers of weight, displacement, and or foreign to the model. That's a lot of things to consider, since there are, if we might add the second, third, or fourth power of either weight or displacement or foreign, that's a lot of possible combinations of additional variables to add to the model. But a rule of thumb is that you don't add a third power of a variable to a model unless you've already added the second power of that variable to the model. It's not a hard and fast rule, but it often makes sense, given that if the third power of a variable influences a model, it's probably the case that the second power does as well. And in order to kind of step intelligently through all possible combinations of new powers of those independent variables, you might want to use a stepwise regression technique, which is controversial for other reasons, but it might be one way to kind of investigate which additional powers of the independent variables you might add. I'll argue, again, as usual, that the best reason to add a power of an independent variable to a model is because you understand some sort of economic, financial, or physical reason, some theoretical reason, why that power should perhaps be added as a new independent variable in your model. So all we do to implement the OV test is to say estat OV test or OV test, and here's the result that we get. We have a null hypothesis that the model has no omitted variables. We see that the name of the test here is Ramsey reset. It uses powers of the fitted values, that is y hat, of miles per gallon. And what we see here is that we have an F statistic with numerator degrees of freedom equal to 3, denominator degrees of freedom equal to 67, and the p-value connected with that F statistic, which is 2.53, that p-value is 0.0643, which is not underneath the traditional significance level. So what this approach suggests is that powers of weight, displacement, and foreign, that is the second, third, and fourth powers of weight, displacement, and foreign, do not jointly add all that much additional explanatory power to the model. So maybe it's not worth considering adding them to the model. Okay? Where does the F statistic get its numerator and denominator degrees of freedom from? Well, the reason for that is as follows. Because the test that is being run is a restricted F test, the 3 here is coming from the fact that we had 4 minus 1 parameters that we estimated. That is 3 independent variables in the original or base model. And in the extended model, in which we add y hat squared, y hat cubed, and y hat to the fourth power, we have 74 minus these 4 degrees of freedom associated with these coefficients that had to be estimated, minus 3 additional degrees of freedom due to y hat squared, y hat cubed, and y hat to the fourth power being considered as being added to this model. So that's why we have 3 and 67 degrees of freedom for the numerator and denominator respectively. So this is a quick run through of the omitted variables test. In this case, it doesn't suggest that we should add maybe weight squared or displacement squared to the model. We could go on ahead and do so and investigate the implications of doing so. For example, if I add weight squared to the model with this kind of command in Stata, so that's adding it on the fly without actually generating a new variable, we actually see that weight squared is a statistically significant contributor to the model. So you might say, well, Jeff, why is weight squared a statistically significant contributor to the model, but why did the OV test not indicate that? Well, the reason is because the OV test uses in Stata y hats, which has the influence of weight, displacement, and foreign in there. And so it's not kind of targeted on one particular variable, a power of that variable. So as you can see, the OV test should be used as kind of a guidepost. It's not going to provide you with definitive answers as to whether or not you should add a squared version of one of your independent variables to a model. But it will, if it rejects the null hypothesis, give you pretty strong evidence that you might want to consider adding powers of independent variables to your model. So that is a very quick run through of the OV test. Let me know if you have any questions.